gentlemen, and welcome to this third day of the 75th International Astronautical Congress. Day number 3, or Wednesday, always is traditionally our Diversity Day, and it has become almost a tradition that the first plenary is organized by our next generation, the so-called Next Generation Plenary, and this is also the case today. The topic, or the title of this plenary, is Intelligent Space, Big Data, Advanced Algorithms, and Autonomous Robotics in Space. The Next Generation Plenary will especially focus on how intelligent systems can operate in the space environment, where there is less data, greater communication distances, and a more extreme environment. For the robotics system, the plenary will also showcase voices from those who are interested in data-driven governance, combating data-based biases, artificial intelligence ethics or laws, regulations and policies of using automation for space environments. You will also again have the opportunity to ask questions to our panels through our Slido system, and maybe we can bring up the slide with the QR code if you don't have it yet. But now, without further ado, it is my great pleasure to introduce to you the moderator of this session, Mr. Ewan Reid. Ewan is founder and CEO of Mission Control, a Canadian space company that develops software for Earth, Moon, and Mars. Previously, he was a mission controller for 10 of the last 12 space shuttle missions at Mission Control at NASA JSC, and designer of lunar rovers for the Canadian Space Agency and NASA. At Mission Control, he leads the team that was the first in the world to send a deep learning AI to the moon, and he will also be announcing today a new AI mission at a press conference at 2:30 in the afternoon. Please join me in a round of applause for Ewan Reid.
Thank you very much, and what a great honor to be sharing this stage today with such a great selection of up-and-coming space leaders in intelligent space. So first we have Dr. Shreya Santra. We have PhD candidate Jack Naylor, PhD candidate Golda Wynn, Dr. Kirk Hovell, and Dr. Dimitri Stafudi. And first we're going to start with Shreya, if you could say a few words.
Good morning to everyone here today. I'm Shreya Santra, Assistant Professor of Space Robotics at Tohoku University in Japan, and I'm excited to be on the stage with my amazing co-panelists. As humanity ventures beyond the cradles of Earth, we must continue to harvest the power of robotic technology that can guide and navigate us in our celestial journey. At the Space Robotics Lab, we develop heterogeneous forms of robots and intelligent control strategies for space applications. We design modular robots that can autonomously identify, extract, and process in situ resources that are crucial for scientific research, for energy production, as well as for the construction of habitats that are as a precursor for human presence on Moon and Mars. A major part of my work focuses on integrating machine learning methods on multi-modular planetary robots that can enable them for real-time fault detection, as well as to adapt to the environment through advanced perception and coordination and planning in a multi-agent system setup. We then test these robots in analog sites, as well as the virtual simulators that we built in our lab. Smart autonomous systems, we know that they really have the capability to improve the efficiency and speed while minimizing the risk and costs involved with the planetary missions. However, there are a lot of challenges in designing these intelligent systems, including designing robust controllers or power-efficient, stable AI algorithms. And I'm excited here to talk about my experience and vision on how these intelligent space systems can play a crucial role and play a very pivotal role in ensuring humans' presence in a more safe and sustainable way in space. Thank you.
Thanks, Shreya. Jack?
Good morning. My name is Jack Naylor, and I'm a PhD candidate with the Australian Centre for Robotics at the University of Sydney. My research is focused on developing representations of a robot's surroundings by modelling light to enable new ways robotic systems can see and interact with the world under complex and changing conditions like those found in space. The next milestone in our space journey lies in our ability to create platforms which can sense, think, and act autonomously, and I'm delighted to be here to explore these ideas with you today. Our use of space is about to change rapidly. From on-orbit inspection, maintenance, and refueling, more spacecraft monitoring our planet, and everything we need to support human lunar activities. Whilst our access to space continues to become easier, the challenges of an increasingly congested environment and the limits of human oversight call for next-generation onboard capabilities. New sensors, algorithms, and ways of interpreting data will drive much of this change. Unfortunately, many of the environmental challenges and risk factors seen in space can also be found here on Earth. In my work, new radiance-based representations, which include dynamic appearance, and sensors like event cameras, not only help us to tackle the challenges of drones navigating around reflections in urban environments, but they can help us to autonomously inspect damage and dock satellites in the presence of direct reflections and deep shadows. Importantly, these innovations will rely on multidisciplinary and international efforts to create robust and safe solutions. The same onboard computation and algorithms which handle autonomy in the Australian outback could help us to avoid catastrophic anomalies during rendezvous in orbit. Our capabilities in terrestrial robotics hold the key to not only addressing these challenges, but redefining what space systems should be capable of. Not only will this help us to protect assets and extend missions with high precision and lower risk, but it will yield the data and insights needed to develop our future space capabilities. This is the age of intelligent space systems, and I'm excited to discuss this here with the panel today.
Thank you, Jack. And we're going to go with Golda next.
Good morning. Thanks for making it out in the rain as well. I took a little bit of a slippery walk here. But good morning. My name is Golda Wang. I'm a PhD candidate at the Massachusetts Institute of Technology, and I work at the intersection of bioastronautics, behavioral science, and human-centered AI. I'm excited to be on this panel here today to actually bring a perspective on human-centered AI and thinking about intelligent systems that don't always replace humans, but actually work in concert with humans. I'm here today because my research is actually focused on using AI-centered techniques, or human-centered AI techniques, to build psychological resilience for our crews that will go into deep spaceflight missions. Space is a beautiful and inspiring place, but make no mistake, it is a hostile environment. When we send astronauts up to the station, and as we envision these futures of Moon and Mars exploration, astronauts will be going into isolated, confined, and extreme environments for long durations of time that will be physically and psychologically demanding for them. To live and work in those environments for those periods of time, they need the clinical support to enable them to operate effectively and efficiently to conduct their mission objectives. And the work I do is focused on augmenting that clinical support when clinicians and patients can't share the same space. Those are in scenarios like spaceflight, but they're also in scenarios right here on Earth where patients may not have geographical or socioeconomic access to clinical care. In my work, I actually study how individual, environmental, and linguistic markers can be used to assess mental state and how conversational AI can support healthy behaviors to counteract these detrimental effects of isolation. In my work, I've conducted research on populations, both in space analogs, like the Mars Desert Research Station, but also in analogous, everyday environments, like patients during the early days of the COVID-19 pandemic. I'm excited to be here to think about this vision of sending thousands, millions of people living and working in space. But to do that, we need the clinical tools to support them, and I think health informatics and human-centered autonomy and AI can help us build that future. So thanks for having me, and excited for this conversation.
Thank you, Golda. Kirk?
Good morning, everyone, and thank you all for coming. My name is Kirk Halvel. I'm the co-founder and CTO of the Canadian startup company, Obruta Space Solutions. Prior to founding Obruta, I got my PhD in aerospace engineering from Carleton University in Canada, where I adapted deep reinforcement learning, a type of AI, to the spacecraft community. This enabled spacecraft to learn on their own how to solve problems, instead of needing humans to tell them how to solve problems. I applied this to the spacecraft proximity operations and docking scenario. Proximity operations are when one spacecraft operates near another one, and safe proximity operations are a necessary prerequisite for spacecraft refueling or space debris removal. Spacecraft proximity operations and docking aren't new, but doing them autonomously and at scale is. Traditionally, a large team of folks would be commanding one spacecraft to fly up and dock with another one, but in the future, with autonomous spacecraft, one person could instead monitor many spacecraft dockings. What makes autonomous proximity operations difficult? Well, one part is getting one spacecraft to sense another spacecraft using cameras. One spacecraft must image the other and process camera images on board in real time on underpowered spacecraft computers to figure out how far the other spacecraft is. Traditionally, this has been impossible, but with the advances in AI and big data, this is now just becoming a reality. My vision for the future includes spacecraft that fly around and dock with each other autonomously, refueling, repairing, or removing space debris, delivering and receiving cargo. How many spacecraft will be docking in the future? I predict hundreds of these dockings per day. And the way we get there is through autonomy and AI. Making spacecraft fly themselves is a transformational technology and is the foundation upon which the in-orbit economy will be built. Thank you.
Thanks, Kirk. Dimitra?
Good morning, buongiorno. I'm Dimitra Stefoudi. I am an assistant professor at Leiden University at the International Institute of Air and Space Law, where I research and teach on space law and policy, and I provide advice on the regulation of space activities. I'm very happy to be part of this panel because I get to share the stage with the impressive people that you heard before, but also because I get to speak about something I'm very passionate about, and that is space law. And I know that law is not the first thing that comes to our mind when we're speaking about space activities, but it does have the potential to influence how space activities develop, and I think this is why it deserves a little bit of our attention at least. When we're speaking about space law, we speak about the rules that tell us what we can and cannot do in outer space, and how actors involved in space activities should conduct themselves. Eventually, it includes some limitations, granted, but this is essential to protect legitimate interests, especially as more actors are getting involved in the space sector and we do more innovative things out there, because this is ultimately a way to guarantee sustainable development. In my research, I focus mostly on satellite applications and particularly the regulation and policy of space big data. In the context of intelligent systems, space big data is what allows us to automate, to predict, to conduct analytics at a scale that we are not able to do with conventional, so to speak, data. In order to realize the potential of space big data, we certainly need first and foremost the data. On one hand, we do have several satellite systems that provide us with Earth observation data, GNSS data, increasingly also connectivity. But on the other hand, we have some laws that may limit how we can use, access, distribute this data. To give a couple of examples, we may face intellectual property implications that may allow us, may not actually allow us to create value-added products from the data, or if we do create them, we are not able to further disseminate them. Or we may come across cybersecurity regulations that require us to take specific measures to guarantee that we have the flow of data that we need. But that is just to give you a flavor of the role that law is playing in this regard. I'm very much looking forward to discussing this further in this panel and see what space big data can do in our quest for developing space activities and especially enhancing the benefits we get from these activities and, of course, the role of the law in this regard. Thank you very much.
Thanks, Dimitra. I'm really excited to hear the conversation that follows now. Shreya, I'm going to start with you. What are the advantages of introducing intelligent autonomy in planetary exploration?
Thank you. That's a very good question. So now, as we go on with the private and commercial activities in space as well as on the moon or Mars, we are looking into multi-agent systems working together and doing certain operations like setting up habitats or deploying infrastructures. And here is where we need the autonomy and proper coordination between the agents. This helps them to adapt to the situation, to the dynamic environment, as well as this can be scaled between the agents so that the skills can be transferred between them. So we really need to focus more on how the multi-agent systems can coordinate together and be in a much safer and intelligent way they can do their tasks.
Thanks, Shreya. Golda, I'm going to come to you next with the same question from first robotics to the human perspective. So for you, what are the advantages of introducing intelligent autonomy in planetary exploration?
Yeah, so this is on. Yeah, so I think in terms of planetary exploration, I think I come from the side of if we're thinking of human interplanetary exploration, and as we're thinking about sending people deeper into space, I think all of you know about the communication delay between Earth to Moon, Earth to Mars. That's 5 to 20 minutes one way. That means 40 minutes at most round trip. And then you think about you send a message back to Earth. They got to talk about it too. So then that's probably another 10, 15 minutes to deliberate and then send that message back. So that hour communication is not feasible or practical, especially in emergency scenarios. We think about medical emergencies. Crews need to be independent or predominantly independent. And so having autonomous support capabilities, intelligent systems that are helping them make decisions, execute procedures and tasks, those will have to be embedded onto a vehicle or habitat system. Otherwise, you're solely relying on the human crew member to have all that knowledge and information to execute their entire mission, which is such an intense workload and cognitive load that could be sustainable for a short mission, but if you're talking a long, multi-year mission, that's not sustainable. So I think this development of both autonomy and intelligent systems goes hand in hand with human-centered systems, where if we're going to improve our capabilities for autonomy, that will actually lower the workload for our crew members, but that has to work in concert with each other.
Yeah, amazing. So, and you mentioned embedded, and that leads into the technology, and that flows to my next question, which is both for Jack and for Kirk. So, Jack, I'll start with you. How do you see space-grade computing affecting your field?
I think space-grade computing is the real enabler that we need. So when we think about doing things in space, there's the case of planetary exploration, where we can send a lot of stuff with the system itself. But what we're seeing is, particularly with our reliance on onboard intelligence and edge computing, we can really bring a lot of that. We need that decision-making on board, essentially. For really difficult tasks, for really difficult problems, even here on Earth, we take that off the system itself, process it in a data center, and have some communications relay to be able to do that. In space, that's more difficult, particularly as you get further and further and further from the Earth. So being able to develop onboard computing capabilities that we know are going to be safe, that we know are going to be reliable, that are able to take all the data that we can capture off a system, make a decision, and then interact or perform some action, I think is really critical. We're well on the way. I think we've still got a bit of a road to get to a point where that computation is starting to get to the point where it can interact just purely autonomously on its own. But I think once we hit that, that's the critical enabler. That's really what's going to power intelligent space systems into the future.
Kirk?
Yeah, and I very much agree with what Jack said. We need to have spacecraft making decisions for themselves and processing data on board in real time. This will increase safety and autonomy of satellite systems. And really, typically, space-grade computers have been lacking in their abilities due to radiation hardening needs and whatnot. But nowadays, we're seeing GPUs now being available in space, just as of recently being available. And so we can start to do some AI processing on board. Now, it's still much scaled down compared to what we were able to do on Earth, but we're just sort of at the very beginning of being able to make some of these calculations on board spacecraft in space.
Yeah, thanks, Kirk. So we talked a little bit about advantages of intelligence. We've talked about some of the hardware, but let's take a slightly different perspective and think about law and regulation. So for you, Dimitra, what is the relevance of law and regulation in the development of intelligent systems?
I spoke a little bit earlier about the limitations mainly of law, just to make a strong point about the relevance of law in this discussion. And I think, though, that the contribution of law is in enabling actually all of these things to happen. And I see this enabling in a two-fold manner. One is using the regulation we have to enable the launching of those systems in outer space. And the role of the regulation may be crucial because those are mostly new activities. They are not the same as the communication or the Earth observation satellites we are used to launch into outer space. So the law can play a role there. We see a lot of countries around the world adopting their own national legislation, addressing some of these issues, and therefore enabling all these activities to happen in a lawful, and let me also underline again, sustainable manner. That's also another contribution, I believe, of the law. But on the downstream side, so that's happening upstream, we're launching all those systems. On the downstream side, the contribution of the law, I believe, lies in enabling sharing of information, sharing of data, cooperation. We see that very much in systems that are publicly funded. If I can take an example from Earth observation again, with the EU space program or with Landsat, we have minimal to no restrictions in sharing data, doing whatever we need with data. But it's mostly commercial players that at the moment are the main suppliers of the data that we need. And then we see other restrictions, some of which are grounded in law. And I think there we need a little bit more work to remove some of those restrictions with preserving, of course, commercial interests and so on. But the law, I believe, is just an underpinning of this whole discussion. And it involves limitations, but we're moving toward understanding the challenges and regulating them accordingly.
Well, thank you. Yeah, it's really interesting. And so for Shreya, a question for you. Presuming that we get the policy, the law, the regulatory environment in place, how would you imagine the scenario of planetary robotics in the 10 to 15-year time frame?
Thank you. So as Golda already mentioned, we want to have robots which are human-centric, working together with astronauts and other space travelers. So what I see is having modular, reconfigurable robots that can actually build infrastructures or work with the astronauts for building habitats and transporting tasks and building up rocket launchers and rocket launch pads. We know that we cannot really send a lot of payloads in space. It's very expensive, it's very hard. So the way to go would be modularity, where we can send modules that can reconfigure and do the tasks that they are supposed to do, and they can adapt to the environment, they can adapt to the tasks that they have to do.
Yeah, thank you. Golda, a question for you. This panel is intelligent space, right? And I know I experience this all the time. There's people asking questions. What's autonomy, AI, deep learning? All these things are kind of used interchangeably, and it can be confusing. From your perspective, what are the differences between automation, autonomy, AI, and then where does your work fit into that?
Yeah, thanks for the question. I think actually when I applied to this panel, I wasn't actually sure if they would want me, because I think when we think about autonomy in space, I think we're mostly thinking about like autonomous navigation, autonomous satellite docking, and robotics, but where does the human come in? And it's something that's really, I think all of us coming from academic fields, we see this discourse both in academia, but actually especially the public discourse around AI in the last few years as conversational AI has come into the public conversation, and I think especially in my work leveraging conversational AI. So I think the way I boiled it down is automation is like so let's take the example of a car. Automation is like your cruise control. You set your car to a specific speed that you want it to drive at. Your car understands how to put the car in gear to drive at that speed for a set period of time. Autonomy is then adding a level of non-user input that then the car itself is maybe saying, your Waymos out here, your self-driving vehicles, it's adaptively saying, I want to set the car to this speed based on these conditions around me. I have some decision-making or perception capabilities to make that decision. AI, or sort of artificial intelligence, to me is bringing in what we consider a traditional like human intelligence level of processing or understanding or generation of output. So that would be like if your car is then going to start talking to you and saying, oh, hey, Ewan, it seems like you want to go to the Duomo today. Here's the fastest route. Do you agree? And so having that kind of being able to process that conversation and then respond and then provide those translate those inputs into a system readable input that the car understands, because the car doesn't understand natural language, but then you can translate that into different mechanical or electrical inputs. So that's generally how I break down those differences. The thing is that those Venn diagrams, or it's really an overlap of all those different circles that a lot of us operate in. And so I think the work I do sometimes lives in automation autonomy land. And then when I bring in a human user, usually then that starts to go into AI, machine learning, deep learning land.
Okay, thanks for that, Golda. Yeah, it's really, really fascinating. And it leads me to a question for you, Jack. So Golda talked about there the level going from automation to autonomy and talked about inputs coming in. And so from your perspective, where do the challenges exist in developing autonomous space systems in the sense of the technology? Where are the bottlenecks? Is it the sensors? Is it the data? You talked about computation being an enabler. Where is it?
I think it's a whole range of things. So, when we look at space, it's a complex environment in and of itself. We've got this real challenge where everything up there is very difficult to do, and we have to make sure that it gets done right. So sensors, I think, one of the main things that at the moment we've kind of stuck very, very safe and steady. But I think there's a whole lot more we can exploit there. My lab, for example, is very much involved in developing novel sensors that are suited to particular tasks. The challenge in space is we like things to work, right? We like that flight heritage. So I think The real challenge is not necessarily any one of those components, but it's dealing with the risks of trying something new and doing that in a way that we can then enable that innovation and we can start to really change how things get done. So that means that, being able to have platforms where we can try new algorithms, try new models, see how they perform, really benchmark them and work out where we can improve and iterate along the line. That's, I think, the key bottleneck at the moment. Being able to have that experimentation, develop these new systems, test them really rigorously, and then be able to deploy them on a much wider scale. That's the critical step, I think. Once we've got that, in combination with computing and having sensors suited to the environment, amongst being able to leverage all that data that we can collect, that's the insights we need to have that innovation.
Yeah, thanks, Jack. That's a great answer. Kirk, I'm going to come to you next. You talked about rendezvous proximity operations and docking and different applications that you're looking at your innovative startup. Just take a step back. Why do we need autonomy in space for this?
Yeah, that's a good question. And really, with the falling costs of getting to space, it's really changing the paradigm of how folks are looking to use space in the future. And many governments are also interested in on-orbit servicing, so instead of just sending up a new spacecraft every time it fails, it's much more sustainable and now economical to refuel or repair them. But if we want to have this sort of bustling economy of goods and services interacting in space, we do need autonomy for really three main reasons: safety, scalability, and bandwidth. For safety, we need to be processing data on board the spacecraft in real time. There's simply not the time to be sending data down to the ground, analyzing it, and sending back up, especially once we have greater separation distances and we have delays in that data transmission. So for highest levels of safety, we need to be having more autonomy and processing data on board. For scalability, again, if we're going to be having hundreds of these spacecraft docking every day, it would be very difficult to have huge teams of folks piloting these spacecraft. We need to have a higher level of autonomy where the humans can more so be monitoring the performance of these types of systems. And then for bandwidth reasons as well, there's so much data being generated during these proximity operations and docking scenarios that it's just too difficult or too expensive to be streaming down huge amounts of data constantly. It's much easier to develop an autonomy system to avoid that limitation. So really, safety, scalability, and bandwidth constraints are why I see the need for autonomy.
Yeah, okay. Thanks, Kirk. So for you, Dimitra, we've heard now from everybody there's a need for this autonomy. There's technology that can facilitate it, whether it's planetary exploration, prox ops, human exploration. And you've talked about the relevance of law and regulation. Well, then a question about timing. Should the regulation precede the technological development, or should it go the other way around?
That is the most dangerous question you could ask me, perhaps in this context, because technology is moving very, very fast. I'm not sure whether there is one golden solution, but we have to acknowledge that the law is moving very slow compared to technology. That's why sometimes we may need to preemptively regulate, to ensure at least a minimum level of standards. But doing that, first of all, we have to understand that it's minimum, and we see how technology goes further. And second, we have to understand that it should be limited to what is very necessary to regulate. And that's why we're seeing around the world and also on international level that instead of adopting binding laws, especially in areas that are really moving very fast, we are developing standards, we are developing guidelines, we are developing similar soft law instruments that allow us to understand some needs that have to be somewhat regulated, but at the same time allowing the technology to develop in a certain extent. If I can make a comment, having heard everyone before me, it's always very difficult for any regulation or any person coming to tell you while you're developing your technology that, sorry, this is not going very, very well. So it's better to involve the regulatory consideration earlier in the process, whether we end up regulating or not, at least acknowledging it and see how that goes.
Okay, interesting. For the audience, I'd remind everyone that there is the Slido app active. I've got some questions coming in. We're going to have a few minutes towards the end of the discussion to go to audience questions. So if you've been engaged so far and interested in what folks are saying, please post some questions and I'll filter through and ask them to our panelists. For Shreya, I'm going to come back to you and ask you, from your perspective, how important do you believe it is to equip young engineers and scientists with the skills that are needed to create a sustainable and, again, intelligent space future?
Thank you for the question, and that's a great follow-up to what Dimitra mentioned. As the technology is moving really fast and space is not left behind, and we are looking into distributed autonomy and evolutionary robotics and planetary explorations and sensors, it's very important that interoperability exists between the agents and between the stakeholders. And that's where scaling up and understanding what's going on in the technology sector is very important, so that they can share the information, share the knowledge between each other, and know that their interfaces can interoperate with each other. That's one thing. And most importantly, we are looking into sustainable space exploration. We are looking into long-term exploration. So to ensure the sustainability, we have to be sure that we are really ready. The young engineers and the scientists are ready to move forward, and they are aware of the technology, science, as well as the legal implications that are involved in this. So this is a very important topic, and we should all be very updated and be skilled with the fast-moving AI and machine learning.
Yeah, okay. Golda, I'm going to come to you next. Where do you see the need for human-centered AI versus AI systems that are more intended to kind of replace humans?
Yeah, no, I think that question, I think a lot of the panelists in these answers so far have really touched on where does autonomy and AI that is meant to not involve a human operator, so like on-orbit servicing. Hubble telescope, we sent astronauts to do that servicing, and every time they step out of a vehicle, EVAs, they look cool, they're awesome, I would love to do one day, but that is an incredible high-level risk activity that we are sending crew members to that I think is not necessary, especially in this day and age, as we're really advancing robotic operation and teleoperation. So those really critically thinking about what is the risk to human life and what is the value return for sending a human to do activities. I think it is really interesting and promising to look at the interest in commercial space stations these days and thinking about how we can do on-orbit science, particularly for pharmaceutical and drug development, and thinking about if scientists could go up on those stations and be able to conduct the research that they've been wanting to do, because that microgravity environment is incredibly unique and could deliver solutions that you can't make on Earth. I think those are scenarios where supporting those crew members with autonomous systems and AI and building those systems to meet their needs are really valuable. But in these other sort of, both in terms of low Earth orbit and exploratory missions to Moon and Mars, I think kind of Shreya's point of having both human robotic systems that are in sync with each other and actually in development together in parallel and in conversation is what's really critical if we're going to start sending humans to those distances. So yeah, I think each application space requires some really critical evaluation of where does the human fit in, and if they do, we really need to center them up front.
Yeah, okay. It's really, really fascinating. Jack, I'm going to come to you and ask a specific question that you maybe can answer as opposed to some of the other panelists. In Australia, the space sector is really growing rapidly. It's really exciting. A lot of it is built on kind of expertise in robotics, and I'm just wondering how you think that's going to contribute to this new era of intelligent space.
Yeah, I think it's going to contribute substantially. And the reason why I think that is Australia, we've had a really fast-moving space sector for about the last 10 years now. And year on year, it keeps going. But the thing that I kind of recognise, and I think a lot of people in Australia do as well, is that a lot of that growth is built on a really long history in robotics and associated areas as well. We've got some pretty unique challenges in Australia, pretty similar challenges to what you might find on the surface of Mars. And I think that means that we're pretty uniquely positioned to deal with those challenges and transfer them between that terrestrial domain and the space-based domain. As well, we've really focused on building robotic capabilities working alongside humans as well, so in manufacturing and things like that. So I think we've got a really strong part to play, and being able to leverage that expertise and apply it to this new domain on the international stage, that's going to be a really, really strong part. And I hope everything going forward has some Australian piece of technology that's leveraging that expertise as we move into this exciting intelligent space age.
Okay, thanks, Jack. For you, Kirk, we've heard a lot about the different words here: AI, autonomy, automation. A few times in Dimitra's opening, she mentioned big data. And I think big data is a part of this in terms of training some of these technologies. So, in the context of spacecraft docking and what you're focused on, where does big data play?
Yeah, so big data is critical. When we hear about, the name of this talk, Big Data, Advanced Algorithms, and Autonomous Robots, if we want autonomous robots and advanced algorithms, we need big data. Big data is really the foundation upon which those other two items are trained and built. And in the spacecraft docking context, it's sort of a new area, and there's not a ton of data out there at the moment, but the amount of data collected during each mission is enormous. Just, you can imagine all the sensors, many cameras, GPS, event-based cameras like Jack was mentioning, just creating tremendous amounts of data, which can all be fed into these advanced systems for training. And the more of these autonomous operations we do, the larger our bucket of data grows, and the better that our autonomous robotics can become.
Okay, thank you for that. I'm going to go to some of these really interesting questions I've got from the audience. There are a few that seem to center around the theme of trustworthiness, of trustworthy AI, a little bit related also to the verification and validation process. Kind of how do we know this is going to work? But the one that I think is really interesting is, given these are critical functions, who is responsible in the case of default? And this one's been upvoted a lot. I think a lot of people are interested in this. So Dimitra, maybe I'll go to you. Where does the responsibility lie if something doesn't go the way we planned with an autonomous system?
Whoever gives you a good response to that wins the argument. We're talking very much about this particular question in the discussion surrounding AI that really takes the center stage of regulatory discussions lately in many parts of the world. There are several options, and we have to tailor those options to the system we have in mind. We cannot only blame the system, because that will not give us anything. If you want the system to do something and the system doesn't do it, and you blame the system, you get nothing back. If you blame the entity that created the system, it may be unfair because this entity creates the system to be used in various contexts, so that is counterintuitive to keep developing this. You may want to kind of blame the entities that contributed in the development. It's usually not only just one company, one organization creating an entire system. You may want to blame the user, especially when we're speaking about specific technologies. The way you use them really makes a difference if you use them for a purpose for which they were not built, or for something that the intelligence system is not meant to do. Maybe the fault is on you. We don't have the answer at the moment. I think that it's better to look into the user or into the several stages of creating the system, not to put the blame, but to hold the standards high and to be able to trace back where the fault is. In that sense, we need not a regulation, maybe a guidance to tell us, please keep an eye on what's happening, to be able to appoint responsibility, however you want to call it. But this way, it goes both ways. This way, you can also find the mistake, understand whose fault it was, and improve the technology as well. So it's kind of a circle.
A complex circle. Yeah. Okay, I've got an interesting one here. Gold, I'm going to bring it to you, and I think it's relevant to me and to everyone in the room here. This morning, I picked up our certificate for mission control as being an IAF diversity supporter, something we think is really important. And the question says, this is a very international panel with everyone working in English as the lingua franca. So facing a future with more diverse spacefarers, how likely do you think it is that English human-machine interfaces will exclude people who are not proficient in English?
Ooh, that's a great question, because I think that's a conversation that's happening in the conversational AI space right now of we're building all of these chatbots, and they're all being built in different languages, and there's so much different cultural context in how human behavior changes based on you interpreting that it's an AI system and how you yourself might respond in a different cultural environment. And I think it's something we talk about of if we're gonna send these international crews to, we're talking about these international crews to Moon and Mars, they will need to both team together and understand the different cultures and customs that they're coming from. And I suspect their home agencies or their home entities will hopefully build support tools that can be functional for all crew members, both in the shared cultural context that they'll have to develop and create as a team, but then for individual contexts where that's the personalization that hopefully informatics, big data can give us to tailor tools to each crew member and their needs. But then there needs to be a shared understanding of how we interpret a shared tool. So that's why I think it's important to have the users in the conversation as we're designing these tools, as we're designing the regulations, and we're talking about where does blame lie. Hopefully it is kind of dispersed across, or that when there is blame to be had, we have clear solutions that don't really provide more detriment to the user, even if they are at fault, but really centering how do we have this design, a co-design as we're building these tools so that the users actually have the content that they need.
I like that idea, that co-design and user-centric design, and it's a great question, whoever asked it out there. It's great to see such a big audience. It's obviously an important topic, and I think for us all as an industry, a community, to enable the broadest participation, we want to think about it. So that's great. There's another question here that's been upvoted a lot about whether there's research or industry looking at onboard intelligence, task planning, scheduling. I'd extend that to image classification, et cetera. I won't actually give that to the panelists. I'll just say, if you want to know from an industry perspective about an exciting upcoming AI mission, my company has a press release at 2:30. So that's the answer to that question. And then from there, I'm going to go to Jack and Kirk, specifically called out from another question here. Kirk, maybe I'll start with you first. What do you think is the potential and the challenges of modular space systems, given that that's a growing element within space robotics and ISAM?
Absolutely. Yeah, modular space systems can address complex needs in ways that our current spacecraft can't. So there's certainly a lot of promise in them to be able to reconfigure for new missions, even attach new modules to upgrade systems on board. There's been a lot of interest in sort of the cybersecurity community of being able to upgrade components on board a spacecraft, which can certainly be helped with on-orbit servicing and docking, but reconfiguring certainly adds a huge complexity to spacecraft. And we need a number of, say, docking ports to be able to actually connect components together easily and with standards. There's a number of standards organizations out there trying to develop best practices for these type of docking connectors. And like we were talking about earlier, there's no, regulations are not prescribing you must use these certain docking connectors. It's really letting the industry determine which one is best, and then it'll likely be adopted sort of as like a USB standard that everyone just sort of adopts.
Jack, you want to add to that?
Yeah, I think modular space systems are really going to be how we end up with a mostly sustainable space industry. I'll say mostly there to cover myself. But I think that if we have that capability where if something breaks, we don't just need to go up and fix the whole spacecraft. Maybe we just swap out a component and slot a new one in. All of a sudden, that's a whole new paradigm in how we actually maintain space systems as well. Some of my colleagues back in Sydney, we floated around the idea at the lunch table one day about the idea of, well, what happens if you're done with a satellite, but it still might have usefulness to someone else? Could you go up? Could you take all your software and everything off and then slot in a new computer and sell it on to someone else? Whether that's something that we'll ever end up with. But I think that kind of mindset of being able to go through and replace things, maintain things in a lot more easy to interface with kind of way, that's where we're headed. And that's a really exciting space or direction to be headed in.
Yeah, okay. Shreya, I've got one for you. I saw this slide that you presented. There was a picture of a rover. And so this question says, what potentially useful scientific information, I suppose, or data, could be lost when you have more onboard processing and you're not maybe sending all the data to the ground? What's the risk there?
Yeah, so when we do the mission planning, we have to be very strategic at the very beginning, what kind of data we are looking into and how much of the data has to be transmitted downstream. However, with the advancing autonomy and the edge devices becoming more advancing and more storage, it's possible to also store them on board and have relay satellites or relay spacecrafts with other agencies or other agents that are there and transfer that data back to Earth or back to the control station. If we are losing the data, I guess we just have to accept that we can either imitate that data with the other data that we have, and we can regenerate the data, so we can simulate it as well. So I think that's the main idea. We cannot, space is hard, we cannot expect everything to go absolutely as planned, and we just have to address that in a more strategic manner and see what we can actually achieve.
And if I could just add to that for a moment, there are even some scenarios where folks do not want their data to leave their spacecraft. And so we can keep the data on board the spacecraft and maybe train some machine learning models on board and just export those back down to Earth so that the data never really leaves the spacecraft, but the insights can leave the spacecraft.
That's really, really interesting. Thanks for adding that, Kirk, and thanks for the answer, Shreya. We're coming up to the end. We have a couple more minutes. Dimitri, I'm going to go back to you. So for space law, which is the first step to trace a common line of agreement among different states if each of them has different levels of technology and different short and long-term objectives?
Not if, they do, that is a fact. The first step is for the states, I would say, to share their perspectives so that we understand what everyone is doing. The second step is to go to one of the international organizations we have, or maybe the international organization we have dealing with space-related matters. The UN has a committee on the peaceful uses of outer space that has two subcommittees. One is scientific and technical, where people with that background go and share ideas about how to develop their technologies, what's the future of space exploration, and so on. And a legal subcommittee where we see mostly the strategy and the future of regulation. So that is the first step. Come together, share our ideas, and see what common ground we find. That is, of course, a very noble purpose. It doesn't always happen this way, or it doesn't happen that fast. But this is the first step. This is how we have come in the past, but we're talking several decades ago, with international agreements on space regulation. And in the future, if we do have international law, we will likely, on space, we will likely follow this process.
Thank you for that. we're pretty much at time here. I'm wondering if any of the panelists have any last minute, last comments that they want to make. No? All right, well, that's okay, because we only have 17 seconds left, so I was going to cut you off anyway. So really interesting discussion. Thank you very much for all the panelists and for such a great attendance today here at the IAC. Thanks again.
Thank you.
Thank you.